Alrighty, so welcome to our last lesson for Chi-Square inference, and today we're going to be talking about a Chi-Square test for independence and association. So we have seen when we look at one categorical variable in one population, that is a goodness of fit. When we look at one categorical variable across multiple populations, that was homogeneity. And now we're looking at the last type of Chi-Square, which is indicated when we have two categorical variables or more that are measured in a single population. Typically, one variable will be labeled horizontally and the other will be vertically, and this will give us our table of values, very similar to a two-way table that we've already seen throughout this course. Now, the difference between independence and homogeneity is subtle. For homogeneity, I ask one question in two or more groups, but for independence, I ask two or more questions in one group. So that is a subtle difference. How many samples are you taking? Where are they coming from? How many variables are being measured? Now, they are very, very similar, so you won't get dinged if you accidentally call homogeneity for independence or vice versa, because you can always justify the response, but the true technicality comes down to how many populations are there. So in our state here, we are going to assume that the two categorical variables are independent. We believe they have no relationship towards one another, but we are testing that they are associated or that they are dependent. Our assumptions have not changed. Again, we want some element of randomness. If we're sampling without replacement, we will use the 10% condition. And we're checking large counts by doing at least 5. And we do 5 instead of 10 because I'm not checking a parameter. I'm not checking just one. I'm looking at the overall distribution. So we give ourselves a little bit more leniency with the large counts being at least 5. If these three conditions are met, we'll use a chi-square test for independence. And in our expected calculation here, again, row total times column total divided by the sample size. Here is our test statistic, degrees of freedom found the same way, and then our p-value will be found using the chi-square CDF function. And in the next video, I'll show you all the calculator commands. All right, so students at a large suburban high school take an annual survey to determine problems among students at the school. Each student in an SRS was asked to name one problem at the school, and we have the following results. So here, I took one SRS of this population, and then they were asked the following, right? And they identified these 4 problems. So I have the type of problem, and then I have their classification status. Now, the reason I know this is independence and not homogeneity is because I'm only looking at one SRS, not multiple SRSs. So I'm asked, is there a relationship between the classification of the respondent and type of problem? Is there a relationship? Is there an association? All right, I've got one population, multiple questions. This is going to be a chi-square test for independence. So in my state here, my null hypothesis is that classification and problem type are independent. What I'm testing for is that classification and problem type are dependent. So we go here, and in my plan, I forgot to fill this out, but in my plan, my sample size is about 263, and I labeled that here in my conditions. I took an SRS of 263 students, and it's from a large suburban high school, so I can safely assume there are at least 2,630 high school students in this population. And when I look here at the expected distribution, again, I'll show you how to pull this from the calculator, they're all at least 5. So my expected counts here, again, if I were to multiply the totals and divide by 263, these are the amounts that I would get. Then, if I were to take 24, which is the observed, minus 25, take that difference and square it, divide by 25, I would get what these are called, which are contributions. So when I sum up these 8 values, I get my chi-square test statistic. Conditions are met, we'll use a chi-square test for independence. So here again, if I add up each contribution, I get a test statistic of 15.83. My degrees of freedom, I take the row total, so there are 4 rows, so 4 minus 1, times there are 2 columns, 2 minus 1. So 4 minus 1 times 2 minus 1 gives me degrees of freedom 3. Using my p-value, I'll get about 0.0012. And I obtain that since p-value is less than alpha, we reject the null hypothesis. Thus, there is sufficient evidence to claim that respondent classification and type of problem are dependent on one another. Now, I could also look at a segmented bar graph and see are the proportions the same across both distributions, or is there some significant difference? So that's pretty much the idea. That's the entire unit in a nutshell and the lesson. So go ahead and take a look at the next example here, and it'll just walk you through how to do it. So go ahead and pause the video. Give yourself about 5 to 8 minutes to try this one out on your own. And welcome back. We're looking at job satisfaction versus manager status. So our following two-way table is obtained from a random sample of employees from a company with 2,500 employees. Employees are classified as managers or workers, and then they were asked if they were satisfied with their job. So again, two categorical variables, job satisfaction and then their managerial status or employee status. Next up to our null hypothesis is that we believe that the two categorical variables are independent of one another. It doesn't matter what your position is, that won't influence your job satisfaction. But I'm testing that your job satisfaction and your employee status might have some type of relationship. So we look here, random. We obtained a random sample of 155 employees. 10%, this is a sample and not an experiment, so I need to check my 10% condition. And yes, it is reasonable to assume that there are at least 1,550 employees because I'm told that there are 2,500 employees. And then lastly, for my large counts, I'm going to check the expected. So again, to find that, I take the row total times the column total and divide by the overall sample size total. And when I do that, and here are the calculations for each one, I get the expected distributions. And all expected counts here are at least 5. Now, if I were to look, let's see, is there a big difference between 43 and 30? About 13. Big difference between 37 and 49? About 12. 45 and 58, also about 13. And then 17 and 29, about 12. So a little far off here, so I guess we'll see if our observed difference is pretty drastic. Well, if I take the observed minus the expected, square that difference, divide by the expected, I'll get the contributions. Adding up these contributions gives me a test statistic of 15.76. So to find the p-value, I have to obtain the degrees of freedom. And my test statistic serves as the lower bound. The upper bound is some significantly large number. And then here's my degrees of freedom, and I'm going to teach you this command in the next video. But the reason that the test statistic is always the lower bound is because we know that a chi-square distribution is skewed to the right. So whatever test statistic I get, I'm measuring that or something more extreme. So our test statistic is always going to be the lower bound. So we've got this here. We get a p-value of about 0.00007. Based on the p-value, what should be concluded? Well, since the p is low, we reject the null hypothesis. So there is sufficient evidence that job satisfaction and managerial status are dependent of one another. So I look here, part D, what type of error is associated? Well, since I rejected the HO, this is a type 1 error. Here I claim that job satisfaction and manager status are dependent of one another, when in reality they may be independent of one another. Which means a possible consequence is that someone becomes a manager because they think that it'll lead to a higher job satisfaction, and they could just end up leading to more stress. So that's just a possible consequence of our error here. Now, it doesn't say describe the consequence, it just said describe the error, but it doesn't hurt. So that brings us to the end of our inference for chi-square. So we've learned about goodness of fit, we've learned about homogeneity, and then we learned about independence. So that is going to wrap up Unit 8. And in the next video, I'm going to show you all the different calculator commands that you need. So stay tuned, and thank you so much for Unit 8.